And so guys, welcome to lecture 3 of this NMR lecture series. So on Monday, what you learned was how a signal came about in the NMR spectrum. So any one of these signals that you see here on the spectrum, we showed you how the signal arose. And I'm going to discuss probably in tomorrow's lecture about this, why we have many lines in this signal and why we have many lines in the signal. So there's 3 lines here and there's 5 or so lines here. I'm going to explain that tomorrow. But what I want to do in today's lecture is talk about integration and chemical equivalence. And the first thing that I want to bring to your attention is that in some spectra, you probably see this integration line that you see here. And this used to be, the old way of looking at the spectra. We used to see these integration lines. These days, what we find is that the integration is recorded at the bottom here. And I'll show you just now how to calculate these integrations from this curve. All right, so this is an integral curve. And basically what it does, it measures the area under the resonance or under the signal. So this area here that you're seeing, so this is just an expansion. This here is an expansion of this. So it measures the area under this curve and it represents it as an integral curve. So what we need to do firstly is find out how is this going to help us, this integration going to help us. And the definition of this integral is that it gives us the relative ratio of protons in the molecule, right? So the relative ratio of protons in the molecule can be worked out in this particular setting, right? And I'm going to show you how to calculate that in a second, right? So what we actually do in this particular case is we take a normal ruler. So you can see I've got my ruler here and I measure the integral, right? So I measure the integral. I'm taking the bottom of the integral here and the top of the integral somewhere here. And you can see I'm measuring with my ruler. It's about 22 millimeters, right? So that's my first integral. And I want to see what ratio this integral has in relation to this integral here, because that will tell me the number of protons that this signal has relative to this particular signal. So I take my ruler again and I measure this particular integral. And you can see from the top to the bottom, that gives me 11 millimeters. Right, so I have 2 values here. I have the 22 millimeters for this integral, and I have 11 millimeters for this integral. And you can see now I can take the ratio of this integral to that integral. And that's 22 over 11, or 22 is to 11, which is actually 2 is to 1. And that 2 is to 1 means that however many protons we have here, we have twice the number of protons here. So generally, if I show numbers on a spectrum, you probably will find that we just have a 2 here and a 1 here. So, at many times, we don't expect you to take your ruler and calculate it. So I'll just give you that value 2 and that value 1 and show you that this is a 2 is to 1 ratio that we have the protons. So I cheated a bit here. I gave you the structure on this spectrum. And if you note here, I can't just say that there's 2 hydrogens here and there's 1 hydrogen here. If I do that, I'll be wrong. Because if there was 2 hydrogens here and 1 hydrogen here, that would be 3 hydrogens. And if I look here, I can see there's not 3 hydrogens, but there's 6 hydrogens in this particular molecule, which means that all these integrals should actually be doubled if I want the exact number of protons in the molecule. All right, so essentially here, the ratio of the protons is 2 is to 1, but in actuality, there's 4 protons here and there's 2 protons in this one. right? So we have to multiply by 2 because of what I'm going to talk about now, chemical equivalence and uh, the molecule itself when you look at the symmetry in the molecule, but we'll tackle that just now. So I just wanted to let you know that these numbers don't necessarily mean the number of protons in the molecule. It's very relative, firstly relative to each other, and then relative to the molecule, depending on whether or not there's symmetry in the molecule or not. And this is a prime example, and that's why I chose it's a very nice example to show you that the integration here is not. So in a lot of cases, the integration, yes, is, the number of protons in the molecule, but this is the nice example to show you that in terms of the definition, it's just a relative number, 2:1. So why now is, and if I take it, if I look at this, and in many cases, you'll get a molecular formula, C3H6Br2, right? We'll give you a molecular formula, C3H6Br2. And if you see H6 here, then okay, there must be something that I need to do with these numbers because I've got 6 protons, but I can only see 2 and 1 here, that's 3. I can see half the number of protons, which means I need to multiply that by 2, or there must be some symmetry in the molecule that I am trying to work the structure out. Right? So let's have a look at this particular molecule. And the symmetry here is very easy to see because you have a central carbon atom with 2 hydrogens on it. And that's denoted by A. So if you look at this carbon, 2 hydrogens, I can't tell the 2 hydrogens apart. Right? I can't tell those 2 hydrogens on that carbon apart, so they are equivalent. So I have 1 hydrogen on the carbon here, another hydrogen there. So if I had to draw, a stick structure, you'd see that's how I would really depict my molecule. Right, so if I had to expand the structure, that's how the molecule would actually look. Right, but in many cases, we just give you the structure. We don't, and sometimes we just give you a molecular formula. So I think it's up to you now to take every molecule that you are looking at and maybe do something like this to see very clearly what's going on before you can actually visualize it in your mind and then just work out what it is. Right, so you can see this hydrogen here is not different from that because this hydrogen is next to this carbon and this group. It's next to that carbon and that group, right? And this hydrogen is next to the same thing, next to that carbon and that carbon and the group. And we can't tell apart 2 hydrogen atoms. They are equivalent, right? It's like telling apart 2 soccer balls, 2 identical soccer balls, which are white and has 1 dot on it. You can't actually tell apart the 2 soccer balls, right? So these 2 hydrogens for all intents and purposes are equivalent. And if I look on this side here, so these 2 hydrogens we labeled as A. And if I look on this side, this group, entire group here, the CH2Br group is here. And you can see again that these 2 hydrogens on this particular carbon is the same as these 2 hydrogens on that particular carbon. All right, so the hydrogens here are in the same environment as the hydrogens here. So let's look a bit more closely at what I just said. So I'll pick this particular hydrogen here and see what it's next to. This hydrogen is bonded to a carbon that's bonded to a bromine, a hydrogen, and then this CH2Br group. And if I take this particular hydrogen, it's bonded to a bromine, it's bonded to a hydrogen, and it's bonded to this CH2Br group. So you can see I can't tell apart this hydrogen on my left and my hydrogen on my right. I can't tell these 2 apart because they're next to the same number or the very equivalent number of groups. So because they're next to the same groups, these protons on this particular carbon and these protons on this particular carbon will be equivalent, right? So that's equivalent and that's equivalent. That's why we represent this CH2 group as B, and we also represent this CH2 group as B. So we're using this lowercase letters to show you which of the groups are equivalent and which are not. So this hydrogen is very different from this hydrogen because that's an A and that's a B. And you saw that because this carbon was next to two hydrogens that were next to a CH2Br and a CH2Br. But this hydrogen here was next to a hydrogen of bromine and the CH2-CH2Br group, right? So next to two very different groups. So that's why this is different from that. So if we know that these two hydrogens are equivalent and these four hydrogens here are equivalent on the outsides, on my left and on my right, what you'll actually notice is that I'll just get two signals in my NMR spectrum. And the signals that I get in my NMR spectrum will be due to the central protons on the protons on the central carbon that we denote as A, and the protons on the outer carbons that we denote as B. Right now, I don't need to know anything about chemical shift and shielding and de-shielding that you learned in yesterday's lecture in order to see which is which. But I will just go through that again just now after I make my point about the integration, right? To show you that you can also use what we learned yet on Monday to determine where these resonances lie. But if I just use the integration, I know that there's two protons here and there's four protons on the outskirts of the molecule, leading to the resonance for B. And that is in a ratio of 1:2 or 2:4, right? So the central carbon is the one that has the ratio of one hydrogen, you know, if I take it relatively to these four here, right? So if I look at this central carbon, it must have half the number of protons as the outer carbon. And if I look at my signal here, you can see that this resonance at around 2.3 has half the number of protons as the resonance at 3.4. So this resonance here is most likely to be the resonance for A, and this resonance here is most likely to be the resonance for B, right? Because if I look now, I can see that there's four protons here and there's two protons here in this particular molecule that I have, right? 1, 2, 3, 4. There's 4 here and 1, 2, 2 there in the ratio of 2:1. So 4:2 equals to 2:1. So my A protons lie here and my B protons lie here. So just by using integration, you are able to see where in the spectrum the resonances are. And I can now go and say that this is due to A, my CH2 group, which is central, and this is due to B, the CH2 groups, which are terminal. All right, so that captures what integration is. And probably read up about that. It's not a very hard concept. It's an easy concept that you can actually get to grips with. I now want to just delve back into Monday's lecture and revisit what I said about electronegative atoms de-shielding the proton nucleus and leading to a de-shielding effect, right? And moving the resonance of the signal downfield. Remember that 0 is upfield. As we move toward 10, we're going down, right? So it's a bit of a misnomer that, you know, as you go toward 10, you're going down. But I think you're going to have to get used to now that this is your starting point and you can only go down from there, right? So let's look at every proton environment. And I said I have two different types of protons, the protons labeled A and the protons labeled B. So I'm going to look at these protons labeled A first and note a particular hydrogen. So I'm going to just choose a particular hydrogen from here. I can choose this one as well, right? Because both are equivalent, but I'm just going to concentrate on one for your purposes. But note that this hydrogen is equivalent to this hydrogen. So you're only going to see one resonance for this. Right, and let's see now. This hydrogen is bonded to this carbon, right? And this carbon is bonded to another hydrogen a carbon and a carbon, right? And in terms of electronegativity, we know that carbon is more electronegative than hydrogen, right? So I have this that I'm calling A, the carbon. I've got two carbons here that's bonded to the carbon where the hydrogen is. So I'm looking at the hydrogen is bonded to the carbon, and then I look at the carbon and see what is bonded to that particular carbon. You see I'm going 1, 2 bonds away, 1, 2 bonds away, 1, 2 bonds away, and looking at the atom, right? So I'm always going 2 bonds away and looking at the atom. If need be, I will go to the third bond, but if I don't need to, I'm not going to go to the third bond. I'm just going to go to the second bond, right? So I went to the second bond and I got carbon, carbon, hydrogen. And we said carbon was more electronegative than hydrogen, right? So that signal will appear. And, you know, if you're looking at carbon, hydrogen, we did this on Monday, 2 carbons and a hydrogen, we're looking at, you know, roughly around 1.8 or 1.7 or so. But the fact now that to the third bromine, so you've got 1, 2, 3. 3 bonds away, I have a bromine, I have electronegative atom, right? So 3 bonds away, you've got this electronegative bromine atom, and your bromine is more electronegative than your carbon, right? So that's why this resonance that, you know, where you saw it was around 1 point something on Monday is now shifted to past 2. Can you see now that resonance that you found here? And go back and look at your notes on Monday, and you'll see where a CH2 group with 2 carbons were appeared, right? It appeared somewhere around 1. And then that resonance now is shifted. We call it shifted, right? Shifted from there somewhere around here. And that shifting is caused by the de-shielding effect of this bromine that is 3 bonds away. So I looked 1, 2 bonds away, carbon, carbon, hydrogen. The third bond was to the bromine, and that bromine was an electronegative atom, which was more electronegative than carbon, all right? And that's why you find the de-shielding effects of that bromine atom. Let's look at B. And remember, I'm choosing this particular hydrogen, but this particular hydrogen is the same as that hydrogen, is the same as that hydrogen, is the same as that hydrogen. So although I circled this proton here and I called it B, I could have circled any one of these protons here, this one, or this one, or this one. And I said now this bromine that you saw first for this A was 3 bonds away. But look at what happens now when I look at the proton labeled B. 1 bond away, I have a carbon, right? And there's nothing else 1 bond away. And in most hydrogens, you'll only have a 1 bond away to something, right? Because there's only 1 bond that can be formed with hydrogen. Now let's look at 2 bonds away. 2 bonds away, I have a carbon, just like I had here, I had carbon. So 2 bonds away, I have a carbon. 2 bonds away, I have a hydrogen, just like here. But now look at here. 2 bonds away on this side, I have a bromine atom. And we said that bromine is most electronegative out of this 3 atoms. So here you've got an electronegative atom like bromine 2 bonds away from this hydrogen, right? Here it's 3 bonds away, right? So imagine now the effect of this bromine. Remember that in de-shielding effects, the electronegative atom has a pull on the electrons around this bond here, right? So this proton is embedded in a cloud of electrons, and this bromine atom will pull the electrons toward it. So here, can you see this, because it's 2 bonds away, it has a much greater pulling effect on this proton than it does on this proton, which is 3 bonds away. 1, 2, 3 bonds away, right? 1, 2 bonds away. So a greater pulling effect here. So it will pull the electrons further away from this nucleus here. And if it pulls the electrons further away from this nucleus, remember now that this nucleus will experience a greater effective magnetic field, right? I told you what the effective magnetic field was on Monday. So have a look at that video if you didn't attend Monday's lecture. And this will have a lower effective magnetic field in comparison to B. So that's why this hydrogen needs more energy to flip from the alpha to the beta state, right? And it will be de-shielded. This will need less energy compared to this proton. So that's why we find B so de-shielded around 3.4. And we find A at 2.2, not as de-shielded as B, right? But if I had to compare it for something, if I had a hydrogen here, it will be de-shielded compared to something if I had a hydrogen here, right? So that explains now what the integration is. It also gives you a good explanation of what the shielding and de-shielding effects are with regard to the spectrum that we are just studying. I think I'm going to stop there for a while before I go on to the next part. And then I'm going to take some questions here. Great. So that was the first part of this lecture. The second part of this lecture is tackling these questions. So it's good for us to know, before we even get to look at the spectrum, it's good for us to know how many signals we are expecting in the spectrum and whereabout we are expecting these signals. Because if we know how many signals we are expecting in a spectrum and whereabout we're expecting it, when we get a spectrum from the NMR spectrometer or the instrument, if we made something and we get the spectrum, we can say exactly, yes, I've made it, no, I haven't made it. You know, sometimes students, my grad students come to me with complex molecules and show me a spectrum and say, you know, did I actually make it or not? You know, I don't think I've made it because I don't see this, I don't see that, etc., etc. And remember, when we deal with complex molecules in the higher years, we get a lot of overlap, you know, and what happens in a lot of cases that the overlap that we see sometimes muddies the water, and we don't really, you know, have an easy way of solving the structures. So what I'm going to do now is look at these problems in your tutorial and try to determine firstly if there's chemical equivalence in any of the molecules, and I bet you there are, because we designed it such that there are you know, instances of chemical equivalence here, to see if we can pick them out and then see how that will affect the NMR spectrum. So let's look at the first one. I have 4 carbon atoms here, a CH2, a CH2, and on each side CH3s. So if I look at this structure here, can we see that if I break the structure down and I go through half the molecule, I can get a symmetrical part on, you know, symmetrical portion such that the left-hand portion is equal to the right-hand portion, right? So I've got a CH2, CH3 on that side and a CH2 and CH3 on that side. So if I use the same notation that I used in the previous example, you'll see that I can denote these CH2s as A because they are equivalent. And then these CH3s I can denote as B because they are equivalent. Remember that the hydrogens on a particular carbon are always equivalent unless there's some other extenuating circumstances, right? But generally, in a freely rotating molecule, because the CH3 group rotates around the carbon axis, what you'll find is that the 3 hydrogens average out, right? So the hydrogen at one point in time will be here, and then the next point it'll be there, and then there, and the other hydrogens will all, you know, go around. And at any one point in time, you know, if we take a 10-second break, the hydrogen will pass through that same point in the same manner that all the other hydrogens passed, right? So over time, these 3 hydrogens will be equivalent. All right, so the 3 hydrogens here are equivalent, the 3 hydrogens here are equivalent, and this CH3 group is equivalent to this CH3 group, and the CH2 group here is equivalent to this CH2 group because of the symmetry, right? So if I'm looking at my NMR spectrum, I'm not going to expect to see 4 different signals. I'm only going to see 2 signals. And the 2 signals that I see will be in the integral ratio of 6:4 or 3:2, right? 6:4 or 3:2 ratio of the integral signals. And I explained integration to you just a minute ago. I'm going to go one step further, and in this here, I'm going to say, okay, which one of these signals is going to be closer to 0 and which one is going to be further from 0? So what I'm actually asking you, which is shielded and which is de-shielded here, right? So let's take a closer look at which is shielded and de-shielded. I'm sure you know the answer, but I'm just going to take a closer look at this molecule to show you. And I've got 3 hydrogens here, 2 hydrogens here, and the rest of the bonds, and that is a carbon group, right? So I've got a carbon group here, and the rest of the molecule. I'm not concentrating so much on the rest of the molecule, because remember, I just need to go 2 bonds away. So if I look at this hydrogen that I've labeled as B, I've labeled that hydrogen as B. If I look at that, it's next to a hydrogen, and a carbon. All right, so if I take B here, I can say it's next to 2 hydrogens and 1 carbon. And then if I look at A, right, so this hydrogen A here, if I look at this hydrogen, I can say it's next to a carbon, and a hydrogen. So I can say A is next to 1 hydrogen plus 2 carbons. And all these here, we can see are 2 bonds away. Right, so all these are 2 bonds away. So if I look at this that I have here in this box, and I just interrogate this a little bit further, right, we can see that what I end up with is 2 hydrogens and 1 carbon, and 1 hydrogen and 2 carbons. And I know that my carbon is more electronegative than hydrogen. So the signal that I labeled A will have a greater de-shielding effect, because now these 2 electronegative carbons, I only have 1 here, and 1 hydrogen and 2 hydrogens. So these 2 electronegative carbons as opposed to 1 electronegative carbon here. So these 2 will de-shield or withdraw the electrons from the signal much more in A than in B, right? So these 2 carbons, that carbon here and this carbon here, is going to take the electron density away from A. But here in B, I've only got a carbon here 2 bonds away that can take electron density away from B. So I'm going to expect A to be more de-shielded and B to be shielded, right? So I'll expect A now to be de-shielded, and I'll expect B to be shielded. All right, so A is going to be de-shielded. So generally what I'm saying, if I look at my spectrum, I'm going to find B closer to 0 and A further away downfield, right? And if you looked at the lecture that we did on Monday, you'll see the B might be around maybe 0.9 or so, and the B might be around 1.1 or so. Right? So not a huge effect, right? So this might be 0.9, this might be 1.1 or 1.2, right? But nevertheless, 1.2 is more de-shielded than 0.9. And that's the effect of the 2 carbon atoms taking electron density away from the proton. Right, so that's the first example I wanted to do with you. The second example that I'm going to do now is this particular example here. All right, and if you look at C and if you look at your tutorial, C and E is exactly the same thing, right? It's just here I didn't extend the structures, right? So here I've actually shown you the structure with the atoms all drawn in, but here I just put it into a short condensed form, right? Now, if I look at this, there's no symmetry down here. There's no symmetry down here, right? Because if I fold this in half, these CH2s are different from the chlorines. So I can't fold this. Symmetry means if I fold it in half, it should be one half should be identical to the other, right? So I can't see any symmetry down here, but I can see some symmetry here, which means if I fold it this way, right? So if I fold this molecule that way, can you see now on this half of the molecule, the bottom half of the molecule, I have a hydrogen and a chlorine, and the top half of the molecule, I got a hydrogen and a chlorine. So the top half is symmetrical to the bottom half. So I'm only looking at protons. I don't see chlorines in my NMR spectrum, right? Because we're looking at a proton NMR spectrum, right? So if I look at this particular molecule, I will only see one resonance because this proton and that proton are equivalent. I'll just see one resonance. And will the integration in this case matter? I don't think so, right? The integration won't matter in this case because you only have one resonance. And where there's only one resonance, integration doesn't really matter because you've got nothing to compare it to. Remember that we took a ratio of the resonances before, right? So where you have one resonance, the integral doesn't really matter. And that one resonance is going to be equivalent to or equal or be represented by this proton here, which is the same as that proton. So I'll see one signal in this particular example. All right. And the last example I want to do is this one. All right, so if I look at this particular one and I first try to identify my different groups, I've got a CH2 group here, right? I've got a CH group here, I've got a CH group here, and then I've got these CH3 groups, right? And if I look at my molecule a bit more carefully, if I look at the central CH2 group as being a central CH2 group, right? This central CH2 group, I can see has a plane of symmetry, which means that whatever's on my left, the CH, CH3, CH3 on the left, is equivalent to the CH, CH3, CH3 on the right. So this entire grouping on the left is equivalent to the entire grouping on the right, with the CH2 group being in the center. Right, so that's the first point. And then I'm going to move away from the whole molecule and just look at the grouping. So I'm just going to look at the grouping on my left, which is equivalent to the grouping on my right, so I don't need to look at both. And if I look at this grouping on my left, can you see that in this grouping here, I have a central CH group that has a CH3 on the left and a CH3 on the right, right? So if I'm looking down this axis here, right, I can see that this CH3 and this CH3 must be equivalent because I have a CH group that's here, right? So this CH group that I have here, we can actually see, right? So if I'm looking now at this particular grouping, I can see that this CH3 and that CH3 is equivalent, and this CH2 is CH and this CH is equivalent. And I'm going to try and put numbers to these. I see my screen just froze a bit. I'm going to try and see what's going on. Right, so I've looked at this particular example and I can see that this is going to be one signal A. These CH groups are going to be B. These CH3 groups are going to be the same, but different to this CH and different to the CH2. So that's C and C. So if I look at now what I have here, how many signals do I have? I have an A signal, a B signal, and a C signal. I have 3 different signals. All right, so 3 signals in this case. And these 3 signals are going to be typified by this A, this B, and this C. All right, and if I look at the shielding and de-shielding effects, etc., you'll see that this A carbon, right, that's here, will be the most de-shielded, because this A carbon, if I can take it out from there where it is, and look at what it's next to a hydrogen, it's next to this carbon A, it's next to the carbon C, and next to the carbon C, right? So it's hydrogen there, right? So this hydrogen I'm looking at is B, it's next to this A, it's next to the C and C, right? So it's my B protons, the A carbon, the C carbon, and the C carbon. So it's next to 3 carbon atoms, as opposed to this carbon, the central carbon here, the CH2 group, which is next to 2 hydrogens and 2 carbons. All right, so I've got 3 carbons here, 2 carbons here, and the CH3 will only have 1 carbon, which is this carbon bonded to it. The others will be hydrogens. So in general, when I have a carbon-hydrogen framework, what really happens in that particular case is that the CH3s are going to be more shielded, the CH2s are going to be slightly more de-shielded than the CH3s, and the CHs are going to be slightly more de-shielded than the CH2s, right? So it will go in that particular order, right? So CHs are more de-shielded than a CH2 and is more de-shielded than a CH3. So closer to 0, you're going to find the CH3s, further away the CH2s, and then the CHs when you're looking at a proton NMR spectrum. Good, so I'm going to stop my screen there. All right, so there's my ethyl chloride, and I've just drawn all the atoms in and all the bonds in, so you can see exactly how the molecule is. As I said, initially you will have to do this, and after a while it becomes second nature to just look at a molecule and know how many bonds this hydrogen is away from this carbon. All right, but initially it's nice to do this while you're still studying. So I'm going to pick, so you need to pick a proton and then work out the number of bonds. So when I pick this proton here, I'm actually looking at the CH2 group, right? Because that's one of the hydrogens in the CH2 group. And you'll note that the 2 hydrogens on the CH2 group is equivalent. And then I start to go out of the hydrogen. That's my first bond that the hydrogen forms. And the first bond that the hydrogen forms is to the carbon, right? So that's 1 bond away from that hydrogen atom. So 1 bond away, I have a carbon atom. But if I go 2 bonds away, that's my second bond. And that's the second bond, and that's the second bond. And the second bond is formed by the atom that is joined to initially, and then the third atom, right? So can you see this is my first bond. In relation to this hydrogen, this is the second bond, this is the second bond, this is the second bond. So I have 3 bonds, right? 2 bonds away. So I have 3 atoms that are 2 bonds away. The first atom that's 2 bonds away is a hydrogen atom. The second atom that's 2 bonds away is a carbon atom. And the third atom that's 2 bonds away is the chlorine atom. All right? Hydrogen is electropositive. Carbon is more electronegative than hydrogen, and chlorine is more electronegative than carbon and hydrogen. All right, so in terms of electronegativity series, that's chlorine is most electronegative. And I have a chlorine atom that's 2 bonds away from my hydrogen here. Right, chlorine atom equals to 2 bonds away. And then I'm going to now, I'll use the black pen here. I'm going to pick this hydrogen atom. And this hydrogen atom represents the CH3 group, right? So this hydrogen atom represents the CH3 group. And let me go 1 bond away, right? So 1 bond away is the carbon. 2 bonds away, I have a hydrogen, and I have a carbon I have a hydrogen, I have a hydrogen, I have a carbon. Can you see 2 bonds away? Right, so all these are 2 bonds away. And 2 bonds away, I don't have an electronegative chlorine atom. I only start to have an electronegative chlorine atom if I go 3 bonds away. So let me go 3 bonds away from this proton here, right? So if I go, and this is the black proton, right? One where my black pen is. If I go 3 bonds away, that's first bond, that's my second bond. This is my third bond away, third bond away, third bond away. If I go 3 bonds away from this, right? 1, 2, 3, 1, 2, 3, 1, 2, 3. 3 bonds away, I have a hydrogen here. I have a hydrogen there. I have a chlorine atom there, right? 3 bonds away. So can you see in the CH3 group, I have a chlorine atom that's 3 bonds away, but in the CH2 group, I have a chlorine atom that's 2 bonds away. So the electronegative atom is closer for the CH2 group that you can probably see here, right? And the electronegative atom is further away from the CH3 group, right? That's why the CH2 group is more de-shielded than the CH3 group, because the chlorine withdraws electrons from this proton much better than it withdraws electrons from that proton. So this is more de-shielded, and this is shielded, right? So this is closer to 0, and this is downfield from 0. Good. I think that's all I have time for today. I hope that you enjoyed this lecture. I hope that you look at it again after I put the recording up. And I hope that you go through the material, and I'll see you tomorrow at